Okay, welcome to this video where we are going to be talking about stoichiometry. Stoichiometry, stoichiometry. Specifically, we are going to be talking about relative atomic mass. In abbreviations, we write it as RAM. Other people they say RAM. Okay, so this relative atomic mass, basically, for you to find the so-called relative atomic mass, we normally use an instrument called mass spectrometer. So I won't even focus on that because our main aim is to know how to calculate the so-called relative atomic mass. And how do you calculate relative atomic mass? In simple definition, or rather if you want to know how exactly you do calculate a relative atomic mass, we know that all the masses on the periodic table, they are made up of two isotopes. In short, every element, its mass is the average of a given element of it. So let's say you have an element like chlorine. We know that element chlorine, it is going to have isotopes of maybe chlorine 35 down there 17. We can also have chlorine 36 down there 17. So before I go into my details of what exactly it takes for you to calculate the so-called relative atomic mass, you need to understand the term isotope. You need to understand the term isotope. Okay, the word isotope, whenever we say what is an isotope, based on our grade 12 understanding, is just one and the same, even at the higher level of education. So an isotope, an isotope, an isotope, sorry, an isotope is an atom of an element, an atom of an element that has the same number of protons but different number of mass. So a good example of an isotope, it can be an isotope of chlorine. We can have 35 here, down there we can have 16, and the other one can be the isotope of chlorine again, which is having 36, down there 17. So if you have to check, we're having the same number of protons. Even here it is also having the same number of protons but different number of masses. This actually gives us a meaning to say we have two different. Okay, so like we said, on the periodic table, all the elements are made up of different isotopes. And for you to find the mass number of every element, you'll find that sometimes you can even be getting numbers that are having decimal places. Why? Because it's just the average of two different isotopes. Like for this one, if you want to find the mass number, automatically you're going to add this plus that divided by 2, and that becomes the average of its mass. So this is an isotope of chlorine. We have two different isotopes of chlorine. They're having the same mass number, the same proton numbers, but the same mass numbers. Basically, our main aim is to know how to calculate the relative atomic masses. So relative atomic masses can only be calculated in two different scenarios. What are those? We can calculate relative atomic mass in a case whereby they have given us the average relative atomic mass of a given element or of a given isotope. So if you have been given such a thing and yet they want you to find the abundances of all the isotopes involved in that, or that makes up the same element, automatically we are going to use two different formulas that I'm going to drop down here. So getting an example of chlorine. Chlorine is made up of two different isotopes. One of the isotopes is having a mass of 35 and the other one is having a mass of 36. But they all have the same number of protons. So if you want to find the average atomic mass for chlorine, what do? You have to get the percentage of that one which is having 35 as the mass divided by 100 multiplied by what? The mass. Then you say plus the other one, you say the percentage of it again over 100% multiplied by its mass. So in this case, whenever I'm dealing with these two things, since I have the same bases for my percentages, meaning that what I'll do for me to find the relative atomic mass for chlorine, it must have something like, you say its percentage multiplied by the mass, then you say plus the percentage again for the other one multiplied by the mass divided by what? Divided by 100. This is a primary way of calculating because you have the same denominator, so it won't take you for you to know how to calculate the what? The numerators. Just add the numerators and divide by the common denominator. That is the first scenario. The second scenario is when you have been given the average masses for all the isotopes and you want to find the abundances. So if you have been given the average mass, you want to find the abundances, you do like this. You say RAM, which is relative atomic mass, has to be equal to, then you say X as the percentage of the given isotope, then you say over 100% multiplied by the mass of this element. So here we are trying to find the percentage of this given isotope. Let's say you have chlorine here, which is having 35 as the mass. Automatically you use the same 35, you put it there. But here you want to find what? You want to find the so-called percentage of chlorine into the chlorine as an atom. Then you have to add again plus. So since we have found the percentage of the first isotope, the second one, meaning that it has to be out of 100, of which I'll do like this. I'll say 100 minus x in a form of the percentage, divide by what? Divide by 100. You multiply this by the mass of that given isotope. So these are the best ways that we can use for us to know how to find either the average atomic mass if you have been given every abundance with respect to their masses, as well as if you have been given the average, or rather the relative atomic mass, you want to find the abundances for every isotope. So let's try to solve some of the questions so that we see how this question most of the time comes. So our first scenario is this question whereby they're saying a natural occurring of copper has two isotopes, which is 63 as the mass. Down there we have the proton number of 29, and the other isotope is 65 as the mass. The down part is 29. So these two, they're called isotopes of copper with the relative atomic mass of 62.930 and 64.926 respectively, meaning that the first isotope is having the relative atomic mass of 62.930, and then the last one is having 64.924 as their relative atomic mass respectively. So if the average atomic mass of the isotope of the two isotopes is 63.546, what is the relative abundance? Meaning that they want us to find the percentage of the first isotope into the relative atomic mass given, and the second isotope into the relative atomic mass given. Now, which formula are we going to use? Right. So I know that you are going to use this formula. The relative atomic mass must be equal to, so these are solutions. We have solutions. So relative atomic mass, I must have the relative abundance for the first isotope divided by what? 100% multiplied by what is its mass. In this case is 62.930. Then you say plus. So since we have two different isotopes, what am I supposed to do for me to find the percentage of the second one? Automatically, you're going to say 100% minus the percentage of this. Hence, you get what? The percentage of the second one. You do like this. You put them inside the brackets. Then you say percent over 100. Then you say multiply by the mass number. The atomic mass for this one is what? 64.9 64.926. Okay, so having been given the average atomic mass of the two isotopes as what? As 63.546, then we can say this has to be equal to x over 100 multiplied by 62.90 plus 100 minus x, like this, over 100 multiplied by 64 multiplied by 64.926. Okay, so this shows that if you continue calculating by placing in every value, you'll be able to reach on the final stage or on the final answer as shown. So those are the two different abundances. Abundance simply means the percentage of every isotope in that given average atomic mass. So we have 69.45 as the first percentage of the first isotope of copper. Then the second abundance, which is 30.52, is the second percentage of the second isotope of copper. So these are the percentages of copper in the these are the percentages of two different isotopes in copper as the what? As the element. Yeah, let's try to look at a different question again, which requires us to find the relative atomic mass. The relative atomic mass given the abundances for every isotope, but they want us to find the so-called relative atomic mass. Okay, so having been given this question as the second example, which says an element consists of 1.40% of an isotope with the mass 203.973 atomic mass unit. Those are the units for mass, whereby we say atomic mass unit, comma, 24.10% of an isotope with mass 205.945 atomic mass unit. We also have the other isotope, which is 22.10% of an isotope with the mass 206.9759 atomic mass unit. And the last one, which is 52.40% of an isotope with the mass 207.9766 atomic mass unit. So our main aim, if you want to prove if you're doing the correct things, you need to add up all those percentage abundances and you'll be able to get 100%. If you get above that, automatically you're doing something which is very wrong. So you can pause the video and try to calculate the question before you proceed to the next solutions that I'm going to post. Since the formulas are already there, just pause the video, try to solve, then you relate to what I'm going to solve. So the question is saying, calculate the average atomic mass and identify the element. So the average atomic mass is the one that is going to help us identify the element. You can't identify anyhow, you have to refer to the periodic table. So I'll drop a periodic table so that you check which one is the one which is having that average atomic mass. Let's try to calculate. All right. I know that I've been given so many isotopes with their abundances. I'm sure there are 4 if I'm not mistaken. So I'll calculate based on the same 4 abundances by saying relative atomic mass must be equal to the first percent over 100 multiplied by the mass plus the second one, the second percent, this is my first, over 100 multiplied by its mass, and say plus the third percent divided by 100 multiplied by its mass. Then the last one is the third, the fourth percent divided by 100 multiplied by the mass. Okay, so if you try to refer to the question which is given, this is the question we're talking about. Read it through before I continue solving. Okay, let me try to solve now. So my relative atomic mass must be equal to, the first isotope is what, 1.4 over 100%, so multiplied by its mass, which is 203.973, say plus the second isotope is having 24.10 as the percent over 100, so multiplied by the respective mass, which is 205.945. And you need to add with the other isotope, which is having the percentage of like this over 100 multiplied by its respective mass, which is 206.9759. You say plus the last one, which is having 52.4% over 100. You multiply this by 207.9766. Like I said, if you are to add these percentages, you have to get 100%. Failure to do that, automatically you're almost doing something which is not correct. Okay, so we have the denominators that are common. What do you think are we supposed to do? You can just multiply the numerators, the numerator multiplied by the what? The mass unit. Same applies to this one, that one, and finally this one. Then you say over 100. Okay, so whenever you punch everything on your calculator, you're going to find that the answer is going to be 2.722 atomic mass unit. You are done, just like that. You are done. That is the correct answer. So I'll drop some of the questions below here so that you should be able to try them out and find the answers. Thank you for watching the video. Do not forget to subscribe to my channel. Follow our Facebook page. Then share the videos and wait for the next video under the same stoichiometry as we're trying to progress. I will also drop my line so that whenever you're facing some challenges over the same topic, you can either call me or just hit my inbox, and I'll be able to explain in according to the topic and in a simple way of you to make a simple understanding. Thank you.